Dr. Bharat Kale, Scientist G and Director of this institute. It's my great pleasure to be introduced him for this morning session. Uh, Dr. Kale has completed his master in physical chemistry from Pune University and PhD in material reaction engineering, that is advanced materials in National Chemical Laboratory Pune Chemical Engineering Division. He's having very vast research experience of more than 24 years in a field of nanostructure advanced materials, photonic materials, solar cells, thermoelectric solar cells, lithium ion air batteries, sodium ion sodium air batteries, hydrogen production from semiconductors, quantum dots in glasses, polymers, nanocomposites, chalcogenide materials, and glasses. Also, is having the expertise in magnetic materials, superconductor materials, hydrogen storage materials, fuel cell materials, and many more. Is a visiting professor at different places abroad, University of Leeds in UK, Gracia University, Slovenia, CNU and Korea Research and Technology, South Korea, Itachi in Japan, Fukushima University in Japan. Is a Google Scholar, H index is 46, and more than 200 publications are on his account. Mainly that is advanced functional materials, small nanoscale general material chemistry, chemical communication, green chemistry, energy environment technology, and many more, having the impact factor in the range of 4 to 12. 33 international patents are on his account. Out of that, 4 are US is applied. Number of PhD students, 5 PhD students completed under his able guidance, 7 are registered, and for 3 is a co-guide. Postgraduate student is completed 6 PPR and 25 have done last year projects under his able guidance. The projects completed is 16, having the total budget of 102, and 11 are ongoing projects having the budget is 109 million. Foreign collaboration with United States, Slovenia, Japan, UK, South Korea, France, Spain, Finland, Australia, and Belgium. Total technology transfer are 4. Number of international conferences organized by him are 4 in a summit, and invited talks, more than 100 invited talks he delivered in international conferences and many more in national conferences at various places in India also. Large number of awards are there on his record, like life member of Materials Research Society of India MRSI Award, Vice Chairman of MRSI Pune chapter, Fellow of Maharashtra Academy of Sciences, also the member secretary of the Maharashtra Academy of Sciences, MRSI Gold Medal Award in 2010 of Bangalore, editorial board member of Metals and Material International is a Springer Journal, award of UK award of year 2013 on photocatalysis by KRICT South Korea in 2013, a fellow of Royal Society of Chemistry in 2020, also is a Wismach award in 2020. With this brief introduction of Professor Kale, is going to talk on today's energy materials and processing. I request Kale sir to take a charge of this session.
Can you see the slides now?
Yes, sir. Yeah.
So, good morning to all, and thanks to organizing committee members, Sathe, Professor Sathe, and others members for giving me opportunity to say. As you know, SWIMET is well known in material science, and basically we work on many materials, not only the restricted to energy. Basically, we also work on strategic sector for the ISRO and DRDO for their special type of things. So, as you know, we have 3 laboratories. So one is in Pune, another is in Trichur, and one is in Hyderabad. And Pune, we work on energy materials and all kind of things. Uh, Specialty polymers, specialty organic chemicals, and all these things for electronics. Basically, we work only for electronics applications. Trichy laboratory, we are working on electroceramic, where these PZT materials, then NTC thermistors, where temperature sensors or ceramic temperature sensors, then ceramic gas sensors, then pressure sensors, all kind of things we do that. Then substrates, we required many substrates of ceramics in the electronics like alumina, aluminum nitride, all these things we do in Trichy. Hyderabad, we work on metals. Metal required for the metals means semiconductors, basically semiconductor metals like silicon, then germanium, zinc, of 99.99 and 4N purity to 12N purity. We have a very special facility. We can purify the metals up to 12N, 99.9 and 9, 12N, something like that. So it's very unique facility we have, and we have a good e-waste generation facility there, e-waste recycling facility. Uh, Now in Pune, we have so many. These are the programs. These are the programs. These are the programs we generally we have taken in the three laboratories. One is nanomaterial devices, all kind of nanomaterials we do. Then piezo sensors, actuators, materials for renewable energy, and lot many things we do here: solar cell, fuel cell, then hydrogen, then their storage. Then high purity materials, semiconductors, I already told in Hyderabad. We have ROHS facility, restricted hazardous substances certification we do in Hyderabad. We have a special center of excellence on e-waste recycling at Hyderabad, supported by ministry as well as the industry. Then in Pune, we have rechargeable batteries and additive manufacturing, where these two center of excellence is also supported by industry. Almost 20 crores we have in this center of excellences. Then we also promote startups and incubations in this area. These are the cement Pune activities, basically LTCC packaging, LTCC based application development and materials, means low temperature co-pyre ceramic. See, anything we do in packaging, electronic packaging, we have a circuits, we have many circuits, multiple circuits, and that circuits has to be have to be connected each other, and then register diodes, anode diodes, resistors, all things, all are to be connected in one pack. So that we do in the here with this low temperature confined ceramic technique. This is 2,000 square feet area we have, and 2,000 square feet area clean room we have, 10,000, 1,000 and 10,000 class, and do all operations. That all equipments are in outside, housed in the this clean room. So these are a very this is a very unique facility in the country we have. Then we do all kind of nanostructures. Uh, Basically, nanometals, there are alloys, semiconductor oxides, chalcogenides, glass and polymer nanocomposites. We do nanoparticle alloys, nanoparticles, semiconductor oxides nanoparticles, chalcogenide nanoparticles. Then their growth in glass, growth in polymers also we do. Under renewable energy, we have hydrogen under natural sunlight from water and H2S. Then thin film solar cell, dye-sensitive solar cell fuel cells we do in energy generation. And in energy storage, we have lithium ion battery and materials. We started working on sodium battery materials, so flexible batteries, metal air batteries. So we'll talk more on this today. And sensors we have basically with we is working on gas sensor, LTC based sensors. See, the sensor has to be uh, package of this sensor will be in LTCC based, so they are very sturdy. Okay, like magnetic sensor and pressure sensor, these are generally done in LTCC based techniques. It's very unique things we do. Generally, all imported sensors are coming with this LTCC packaging. So we have planned, we have done something, and now we have planned many sensors to for packaging. And the strategic sectors we work for thermoelectric materials, then radiation shielding materials, and many. There are special polymers, there are special glasses, there are special ceramics with the different compositions. So we reverse engineer and do for that. So these structures generally we produced in our laboratory. Many structures we have done and still continue for variety of applications like hydrogen production, hydrogen storage, battery supercapacitors, photonics, and space material. See, any material with the different structures and nanostructures, they are useful for their the variety of applications. Some of the applications, like some some material are useful for solar light. Solar cells. Same can be utilized for hydrogen generation. Same can be utilized for the uh, um, storage for with do some modification. So this is actually the beauty of the materials. So any device is the backbone of the device is the materials. But unless and until you have good materials, high purity materials with the defect-free materials, will not get the electronic uh, properties, efficient electronic properties, or you can say the word desired properties, which are requiring the special application. So this is the facility we have now. We have a plasma reactor, then LTCC packaging facility. You can see it's in-house in the clean room. We can have this the LTCC tape. This is a ceramic tape you can see of 200 micron size. Then this is a battery facility. Then we work in this battery facility. We are working. We have fabrication facility like pouch cell as well as button cell. We have glass melting facility of special glass melting facility. Then we also work on flexible electrolyte, polymer base, ionic liquid base, and special type of glasses, maybe X-ray window glasses and optical cutoff filters. Then fuel cells, and thin film solar cells. We have a facility, and sensors. Lot many sensors we do on our uh, uh, this is remote Trichure area where we work on supercapacitor, thermal sensors, microwave, all these kind of things we can do there. Then this is our these are the products developed by our Trichure laboratory. You can see that all sensors, then microfilters, BMT resonators. So this, बस ये तो बहुत है तुम्हारी So these are the facilities, and this is CIMET Hyderabad. We are working on hafnium production, high purity materials, silicon carbide, crystal. Um, then we also developed a NAVIC antenna there. These are the very special type of NAVIC antenna, like GPS. We have a imported the American technology, so we can have our own technology with the NAVIC antenna. We can have that. It is a replacement for a GPS. Then e-waste recycling, average facility. So these the hafnium is required in the ISRO for and the in the rocket where the propellant is fed, there the temperature of close to 1000 degrees centigrade. So is hafnium metal, hafnium, zirconium, and titanium. The three metal together, there is alloy formation, and this alloy is used there as a nozzle. Okay, so so these are the important project we have in the Hyderabad. This is a hafnium plant we do, and this is a product developed there. Like I told you that cadmium 7N purity cadmium and zinc, germanium 7N purity. Tellurium can have zinc. You can see the high purity zinc of 12N purity zinc and 7N. We do 7N to 12N, and we can do the granules of zinc for special application. Then this is silicon carbide single crystal electronic devices catering to the defense requirement, because for high power electronics we need the silicon carbide wafer. So we worked on that and we got a very good results out of it. And we now this will be useful for the e-vehicles. Now e-vehicles will be having high power electronics, so they need this kind of wafers. And so, and the energy and the environmental energy issues we are tackling. We also work on the sensors for this pollution and air pollution as well as water pollution. And for energy, we have so many options. We are working in four directions for the energy applications. But basically, we are going to talk today the hydrogen and battery. So today you can see that the energy generation we have solar cells, nuclear, thermal. So we are also working on thermoelectric fuel cell, and majorly work on hydrogen. And their energy storage in energy storage we have hydrogen storage, and capacitor, battery, and hybrid system. So battery along with supercapacitor and along with supercapacitor can enhance the storage capacity. So that is that work is also going on. We have one project. So why this nanoscaling is important? Because the high surface area tuning of with this decreasing the size of the particles or increasing the particle size or tuning the particle size, we can tune the optical properties. Even electron properties, in some of the cases it changes, and that we take the advantage of that. And all this we have the advantage in the miniaturization of devices. So this is useful for agriculture, automobile, electronic devices like mobile, solar cells. Everywhere we are talking about it. And just follow quicker me. Chat. And as I showed that shapes and size, and how shapes and size are important, that we can. So we work on the rods kind of structure, wires, plates, triangles, poles, all kind of structures. Our students are working on that, and some of the structures very useful, like honeycomb like structure, very useful for our battery applications. So how this nanostructuring nano size effect, we can see that it's not working. You can see that how this 1 nanometer, 2 nanometer, 3 nanometer, and bulk. You see the energy difference here with the size. So we have very small nanoparticles with a huge energy generation, and this energy can be utilized for excessive energy, can be utilized for so many in many applications. this is a this is a very typical example that how this optical property changes, like with these quantum dots of CDSAC from 2 nanometers to 6.5 nanometer. We can have 7 colors in the size, and that's why it can be used for the your displays, and the display technologies can be uh, these quantum dots can be used in display technologies along with polymers. So this is electronic packaging from, so earlier we were talking about some 32 nanometers. Okay. 3,200 nanometers to we came to 32 nanometers in 2015. Now we are talking about 3.2 nanometers. So this packaging up to at nanoscale with the LTCC packaging, and now we are also MEMS packaging. We have started so that we can miniaturize the size of the devices. So for this, we required nanoscale materials in huge quantities. So this is one of the process we developed very small size cadmium sulfide in large quantities. We can have 5 nanometers of cadmium sulfide at in large quantities, maybe 500 grams or 1 kg batch. So they are very typically you can see that the size is maybe 20 nanometers here, 5 to 20 nanometers, and quite uniform. This again, same combination of cadmium sulfide and cadmiums with tuning of the band gap also gives a good particle size. And huge quantities if you want to make. We have nanometals, and we can make nanometals, nano oxides, and nitrides using this plasma reactor. The plasma system, you can see that plasma system, you can go to the temperature goes to 3000 degrees centigrade. One of the reactor is the cathode here. Like suppose you have to make aluminum nanopowder, then you can have aluminum cathode, and this can be temperature goes to 3000 degrees, and aluminum is get vaporized, and it's quenched at molecular. So we get the quenching temperature gives the particle size. Determine the particle size. We can suppose this particular size is required, then we can optimize the quenching temperature and quenching time. So this is a 5 crore equipments we have installed in our laboratory, and they are this is very useful to our strategic sector. This is aluminum powder. Though you see that bigger balls here, but these balls nothing but the hollow balls, and with very small particles deposited on this. So this is the aluminum nanoparticles. So we have made with plasma reactor. This is copper nanoparticle. Very small nanoparticles up to 200 nanometer size scale. Though we see these balls, we have a lot of many nanoparticles are deposited on this ball, and inside there is the ball here also. So the advantage of this plasma reactor is we can get the uniform particle size like this. This will be useful for this copper is used in the propellant as oxidizer, copper and aluminum. In propellant, generally they use aluminum, copper as a oxidizer to increase the fuel efficiency. Almost 30% they are using these nanoparticles, copper, micron size particles. Now they are using nanoparticles. So the because of the volume and weight has been reduced from 30% to some 10%. It has come down to 2%, 10%. So that is the advantage they have. This is the bag. You can see this copper nanoparticle. When the size of the nanoparticle is so small, when you open this bag, automatically this gets oxidized. This is the exothermic reaction. Temperature goes to 800 degrees centigrade. It becomes red hot when we open it. Now this is a sealed plastic. It is sealed in plastic. So the exothermicity, you can see the oxidation of exothermicity of copper to copper oxide. Uh, that indicates that the copper has been, nanoparticles have been formed. So this is the dendritic structures we require for some of the applications in the antibacterial, as well as we also use in battery. You can see the hexagonal cobalt nanoparticles are assembled in the form of dendritic structure. And this is basically, it's very important in the thin films of this cobalt, because such kind of films are very important. So,
हो मला सुदीप म्हणाले की 11 वाजता येणार आहे.
चहा मागवा नाही.
हो सांगतो.
These are the structures we make for many applications. This is ZNO nanowires. There is a secondary growth of this. This is initially you can have ZNO rods with hydrothermal reaction, and this then it's again do the sonochemical reaction or hydrothermal reaction further with um, growth directing reagent. We can have this kind of dairy structure. It's very good for the sensor application. During this optimization, we found that when we do the hydrothermal reaction, we have the nanorods, uh, nanorods, and these nanorods can be etched with excessive of alkaline medium, and we can have the hexagonal cups kind of things. So it's very interesting. We found that we published in Crystal Engineering how this growth is happening or something. So the first application of nano coating is we did the first one. This is lead apron. We replaced with nano coating of mixed metals. These 100% X-rays can absorb this. And weight, you can see it is 5 to 7 kg and only 2.5. So this is the weight difference, because the lightweight is very important for this apron. So because doctors are during operation during operation they are wearing this very heavy one. They had a neck problems and all this that can be solved with this very lightweight materials. These are the sensors. Already I told that these are basically sensor, NOx sensors we developed for ISRO. We have demonstrated that from you can see the response time is 1 second. It's very good. Recovery time is 10 seconds. Sensitivity is from 10 ppm to 100%. And ISRO has ISRO needs this kind of sensors in their explosive plant. So we now we are helping them for packaging it in a nice form to them for this their small size. As you see that we also have the nanoparticle in glasses, very unique things we do. All chalcogenide semiconductors can grow in the amorphous materials. Like glass is amorphous. In the amorphous glass, we have crystalline CDS. The important thing here is the 2.5 nanometer to 5 nanometer size, even in bismuth or 11 nanometer size, we can grow in the glass as well as in polymers. This is typical glasses, the cadmium sulfide image. So initially it is a transparent, then you have cadmium sulfide as 2 nanometer, 5 nanometer, and how the size in as size their color changes when their optical property changes. So we have application in the optical cutoff filters here from 400 nanometers to around 800 nanometers for electronic application, which are imported now. Now we have indigenized. Considering their band gap, we also thought that whether we can use for this something else. Now I will talk about this later on. Then these are the special applications for. See, generally, lead glass is used for the X-ray absorption, but we shall prove that these small nanoparticles of only 1 or 0.5% in the glasses can absorb all kind of X, all X-rays and gammas. And we can have the windows, glass window. This glass window can absorb the gamma rays and uh, X-rays. So this is very US patent we have taken on this. Then same quantum dots of bismuth sulfide in glass work like as a single crystal of garnet-like thing for the optical current sensor. So we are making this optical current sensor with these glasses. Generally, it is made up of uh, single crystal garnet. It's very expensive. Basically, how this see when gamma rays are pass, and this how this nanoparticles, when it is a very small nanoparticles, so packing of these nanoparticles layer, maybe in 10 mm of glass, we may have thousands of layers of nanoparticles. That is actually the suppose some rays excess in first layer, they get absorbed in second layer, third layer, fourth layer. So that's why the X-rays are get absorbed within a very small glasses. That is possible because of this mechanism. However, this physics of this we are looking into the simulation, how we can model it. That what we do. So we have a solar cells, solar like single silicon solar cells. Already we can see that single solar cells have guaranteed efficiency of 12%. So second generation solar cells, we are working on thin film silicon amorphous solar cells and cadmium telluride and copper indium selenide. So this is second generation solar cell. And third generation solar cell, perovskite solar cell and Dyson systems. So these two technologies already people are working on it. But now the third generation, we are working on perovskite cells and Dyson solar cells. Even hybrid cells, then polymer solar cells, quantum dot solar cells. These routes we are exploring for high efficiency. Our targeted efficiency will be 20 to 24%. By all these routes, whether we are going to get that we'd like to explore in future. This is hybrid solar cell, like hybrid solar cell based on organic polymers and nanoparticles we are making. Very basic things we did, like we have used cadmium sulfur, cadmium selenide, then AG2S, SNS2, and cadmium. So all these materials we have used for making these thin film solar cells. But still, we have the issue of the efficiency. We are not going beyond 3 to 4%. So we need more experience on fabrication. We have to do many experiments on fabrication and solve the problems. Then this is again the all these DSCC application licensing sources. And we found that different shapes and different nano size definitely helps in the DSCC, because in dye-sensitive solar cell, the absorption of dye is important and absorption of sunlight is very important. So this particle size and shape really helps to enhance the specification. The hydrogen economy, you can see in the future, we have uh, the alternative energy is the hydrogen, because it's energy rich, hydrogen energy rich, and very small amount of hydrogen can be more energy. Now today we are facing problem of cheap cost of hydrogen. So whether we can make hydrogen at cheaper cost using photocatalysis or photosynthesis, and how we can store the hydrogen. So this is very important. So we made attempt to see. This is the actually commercial process, steam reforming of methane, and you see we we get CO2 always as hydrogen. So separation is a problem, right? Temperature, high temperature reaction and separation. So it adds cost for hydrogen production. Then Claus process. The H2S is used. Lot of H2S is produced in the refinery. Whether that can be converted into hydrogen instead of like Claus process. We are getting liquid sulfurs and water, right? So and it's very expensive again. Very clumsy process and energy intensive process. So whether we can have H2S into hydrogen and sulfur. So this is a simple process we are talking today, like whether H2S can be split into hydrogen and sulfur with photocatalytic process. So photocatalytic process is just a different process as compared to normal catalysis process. Because in catalysis we work on the active sites, but here it is actually the electronic phenomenon. During photoexcitation, the electrons and holes are generated, and these electrons and holes are responsible for the uh, reduction and oxidation. Then we are making the strategy how more sunlight can be absorbed, more hydrogen, more electrons holes can be generated, and for the reduction we need the electrons, and for oxidation we need a hole. So we have to we just need to trap holes when we want the reduction, and we don't want oxidation. Electrons has to be trapped. So this combination has to be worked out during the process. This is the first catalyst we produced, and see where is the marigold type of structure which gave good photocatalytic activity. You can say 2000 milliampere, 2000, 3000 milliampere hour per gram. We have produced sorry. We have produced the flower-like structure as well as the nanotubes kind of thing. So both gives a good photocatalytic. Then this is a very phase pure compound, a new compound we have developed. We have made the structure, crystal structure. We have done the crystal structure and all these things. And this is we found this structure is a very stable structure and give a very stable photocatalytic. Then, as we first time we have embedded AG303 nanoparticles in this is the first report we can find in the literature that AG303 nanoparticles can be embedded in glass, which gave good photocatalytic activity. This is the silica glass, silica and phosphate glass. In the silica and phosphate glass, we have grown AG304 crystals, and we can see with the growth, we can see that there is a change in color, and there is a change in optical property. Then we made hydrogen in bigger scale with this glass, because this glass has a band gap, different band gaps from UV region to almost visible IR region. So mixture of these band gaps, glass we use for hydrogen production, and it gives huge hydrogen generation due to the absorption of the glass, absorption of the light, spectrum of the visible and IR. So still we are working on that, whether we can wait for commercial application. So we use all these structures for this hydrogen production, and we found that these structures are good for commercial applications. And now we are going for energy storage. See, as you know, we have the fossil fuel is going down, so and their price is also going up. So battery vehicles and other vehicles are coming in the market. Very safe. The energy is stored in the batteries and supercapacitor. This can be utilized for the e-vehicles and all these things. So that is now up till 2030 we have to we have planned that at least 50% of the vehicles in the country will be on battery. So battery again, the energy dependent application like cathode, anode, and electrolyte. If they are in good quality and their structure is defined, very defined, distinct structure is there, then and then it works and we get the good capacity of the battery. So this is actually the mechanism of battery. I don't know. We have one cathode, anode, and then here is electrolyte. When we charge the battery, ions goes from cathode to anode and while discharging from anode to cathode. That is one cycle. So the performance of the battery depend upon the cycle. How many cycles we can have? Maybe 500 cycle is a better stability. This I already told that how this lithium-ion battery works. We have a cathode is the lithium cobalt oxide, anode is the carbon. So how this while charging this we get lithium ion which goes to the anode and one electron which is connected to the circuit. These electrons. And this again while discharging the lithium ion is lithium ion transported to the cathode along with electrons. So there is a this cycle it is connected to the electronic circuit so that the electrons release the electrons. We get a voltage voltage and current. Actually this reaction is basically how the transportation of lithium from cathode to anode, anode to cathode. So that process should not be disturbed during cycling, and it depends upon your material quality and their structure. We have a cylindrical cell like this and pouch cell like this. In your mobile, we have pouch cell like this. Number of cells are stacked, maybe 24, and here almost 36, 36 single cell are stacked in cylindrical cell. So this is our cell fabrication process. The button cell we can fabricate with I think it is a 32 32 mm size. We can make it in, and bigger size also we can make it. We also make pouch cell here. And these pouch cells we have made with our own material, cathode and anode material we have developed. And we have also made the power bank of 1000 1 ampere and 2 ampere. Also going for now 5000 milliamperes. And all these structures we use for this lithium battery for anode battery, and they are battery. Then we have also made some organic electrodes. This is one of the organic electrode we have. One of our student has fabricated, and it showed good performance. You can see the specific capacity from 150 milliampere hours per gram to 200 milliampere hours per gram. And we have made 100 cycles. Cycle also it gives almost 80 milliampere hours per gram. That was our. That is interesting actually, and still we have to refine how we can make their structure quite. Now this structure is a layer structure. Because of that, we are getting the good capacities. Then also we also made a solid state battery. We have made a polymer electrolyte. Now we have generally now in market we have only organic electrolyte. Because of that organic electrolyte, we cannot charge the batteries fast. Now we are working on the solid state electrolyte so that we can charge the batteries fast. Okay, so this one of the electrolyte we have used, and we found that we get good capacity around 128 milliamperes. Now we are working on the stability of this electrolyte. So we have made using our facility, we have made the two-wheeler battery. Here you can see, and we have run the vehicle with this with our own material with own battery. Weight is only 3 kg. It's much lesser as compared to other batteries. Then it's nanoparticle coated antibacterial antiviral mask we have made during this pandemic situation, and we transfer this technology. Thank you very much. I think this is the very I have summarized all energy materials, their energy generation and energy storage materials, as well as the devices and their performances in large scale. So we hope if you have any questions, you can ask. Yes.
I'm going to unmute all. If anybody is having any question, you can ask directly.
Yes, sir. Myself, Dr. Pankaj Kumar Singh from IIT BHU.
Yes, sir. Brilliant.
Your presentation was nice. At last, you have mentioned mask made from the nanoparticles.
Yes.
My simple question is, as the negative effect of the nanoparticles that is causing the lung problem also, how it will be rectified by using such type of mask?
Actually, we have quoted on the bottom. This one. One is there are two layers of cotton, cloth, and the upper layer of the cloth we have coated these nanoparticles along with polymers. So these all nanoparticles are embedded in the polymers, and these are used in the cotton cloth on the upper layer. Inside there is another layer where it is actually, this is for safety we have done that. Actually, there was no problem because when we wash it, there was no. For I think we have done almost 15 to 20 washes for this, and we retain the same structure of the nanoparticles and same nanoparticles cotton. So,
Sir, which nanoparticle you have used in the mask?
we have a combination of 2-3 materials. It is bimetallic nanoparticles.
Means composite.
Composite, yeah.
Okay.
It will come in the market now very soon.
Mhm.
We have supplied to all hospitals and everywhere. Almost 10,000, 20,000 we have made it here and supplied to hospitals and NGOs. And now we are also working on curtains of the hospitals where we can coat their curtains with these nanoparticles.
Okay. Thank you, sir.
Any other?
Sorry, I had a very less time today because of some 2-3 meetings are lined up today. Okay. Otherwise, I would
No
have
problems. I know your busy schedule.
elaborate.
Tomorrow again function is there.
If somebody wants to have something, we can always do that.
Yeah, what I will do, I will drop your email ID in a chat box.
Yeah,
And then if anybody is having any doubt in future, they will contact you directly.
Definitely.
One question is there. Madhu Ganesh asks, Doctor, how India should be going ahead to increase energy efficiency?
Yeah, energy efficiency means in solar cell, or what is energy efficiency, or
I think she wanted to ask like in a broad concept, overall energy efficiency.
Overall energy efficiency, if you are talking about solar cells, still we can say that um, uh, we have only one option like silicon solar cells because they are cheaper. Only disadvantage is only the size of the panel where uh, we are thinking to work. We have to work more. So the other options like now is a 12% efficiency, guaranteed efficiency. We need to go up to 25%. Then we can the energy it will be very efficient, and with a smaller panel we can have the uh, uh, more energy. And if he's talking about energy storage, then energy storage in batteries, I can say that see now uh, the storage capacity is 120 milliampere hour per gram, which needs to be done up to 500 milliampere hour per gram, which really gives the boost to the automobile industry because when then it in one charge it may go for longer distance, maybe 500 kilometers or 600 kilometers. So that is the objective. Keeping in mind that objective, we are working. It will be in the other form, like whether we can modify the material, or whether we can develop the new material. Okay, or we can say that whether any other option to increase the capacity of the battery. So all these are going on. Like in solar cell, we are talking about perovskite solar 18%. Then quantum dot solar cells, where people are silicon quantum dot hot color solar cells, hot carrier solar cells. People are talking about 61% efficiency, theoretical efficiency. We are not getting that much, but whether we can achieve that 50%, around 30% efficiency. So in that direction, work is already going on in storage as well as energy generation. Both energy generation, another options we are looking for today is whether waste heat can be utilized for energy generation, like thermoelectric. So we have a lot of sunlight in the whole year, and heat is around everywhere in the atmosphere, in villages and all this. Whether that can be utilized for the energy generation, at least at village level or something. So that thing is also going on parallelly. Now the efficiency is low for the thermoelectric. If we can really develop good modules of thermoelectric with refined stacking of the single cells, or we can say uh, good quality thin film fabrications in the PN junctions and all this. Definitely, that will be also another option for the energy uh, generation, because like country like India, a lot of sunlight is available, and hydrogen. We can say that hydrogen is one of the best energy source, and now we are exploring that all the um, our refineries also now have the special hydrogen production, hydrogen R&D in their campus for the future technology of the hydrogen. So I think this will again after 10, 20 years we may have this hydrogen energy in the very efficient way. Basically, it is the green energy. So that will be that is our again the another option for efficient energy for the. Okay, I told him that both the energy generation as well as the energy storage, both is required. And we have to go in both the directions.